So I think the order of difficulty of the exams is, I think exam 1 is the easiest. I think exam 2 is the hardest by far. And then exam 3 feels like it's between the first two, but closer to the difficulty of exam 1 than exam 2. So I guess. Exam 1's down here in difficulty. Exam 2 is up here. Exam 3 is more down. Like the third exam will be easier than this one. So I think about 5.1, just a good way to start, is I'm going to sing hooray for dot products. You guys remember what a dot product is?
Yeah.
So if I want to do, that's what we can use it for. So how do I do the, what's the dot product of 1, 2, 8? So the actual calculation is I do 1 times 3 plus 2 times 4, which is 3 plus 8, which simplifies to 11. So is one fact that we had. How can we tell if V is perpendicular to W?
The dot product is equal to 0.
So I'm just going to spend several minutes telling you everything I like about dot products. And one thing I like about dot products is they're perpendicular detectors. So if I take a dot product and get 0, that tells me the vectors are perpendicular. Let me show you another thing I like about dot products. Is what does the double bar mean? The magnitude. Which is the fancy way of saying length. Then the magnitude essentially comes from the Pythagorean theorem. So the vector looks like 3, 4 up like that. I'm going to break this down. 3 in that direction and 4 in that. And then Pythagoras tells us that the hypotenuse is square root 3 squared plus 4 squared. But if we write this out a little bit, so instead of 3 squared, I'm going to write it as 3 times 3, instead of 4 squared, 4 times 4. Is this looks like a dot product to me. It looks like 3, 4 dotted with itself. So I can also use a dot product to find magnitude. Because the magnitude of a vector is the square root of the dot product of V with itself. compute cosine of theta with the dot product in two lengths. And can you compute lengths with dot products? So, or another way we could say it is theta is the arc cosine so it's really, if I go through the derivation, it's really the law of cosines. Black box that, trust me. So I can find angles with dot products. So even better than just a perpendicular checker, I can actually find the angle. And let's talk a little bit more about this. So do you know that the lengths or the magnitudes of vectors are always positive? And if I have a first quadrant angle, is cosine positive or negative?
Positive.
And if I have a second quadrant angle, cosine is. So if I end up with a first quadrant angle here, cosine is going to be positive. A second quadrant, cosine is going to be negative. And the bottom is guaranteed to be positive, so it's just the top that's going to determine whether it's positive or negative. So what I have so I can use my dot product as a perpendicular detector. If I get 0, another perpendicular. But if it's not 0, it's either positive or it's negative. The positive means cosine was a positive number, which gives me a first quadrant angle. If the dot product is not 0 and it's negative, that must mean that cosine is negative. I got a second quadrant angle.
So do we get other like sine, other sine others?
No, with dot product. So for your Calc 3 fans, do you know about cross product? So cross product has a sign. What's better, dot product or cross product? Dot product. So dot product will work with any dimension. For you Calc 3 people, cross product only works in dimension 3 and dimension 7. Like dot products, more general. Some more stuff I wanted to do, show you about dot products. Give you some more vocabulary first. Don't these always start off easy? We'll get harder. First lecture of each chapter is always straightforward. So one thing is I know my U's and V's look similar. So I try to use V and W when I'm talking about generic vectors. Those are easy to keep apart. And U is I'm going to reserve for a unit vector. What does it mean for something to be a unit vector?
It's negative. So it's a V?
That is a U.
You can square both sides.
So if it's a unit vector, a good way to check is to just take the dot product of the vector with itself. More words? this would apply to any set of vectors, but we're always going to refer to bases with this. So some bases are nice. So this could go up to any size n. I'll show you three of them. So two words is some bases are orthogonal and some bases are orthogonal. So orthogonal are U1, U2, and U3 are all perpendicular to each other. So I think the order of difficulty of the exams is, I think exam 1 is the easiest. I think exam 2 is the hardest by far. And then exam 3 feels like it's between the first two, but closer to the difficulty of exam 1 than exam 2. I guess. Exam 1's down here in difficulty. Exam 2 is up here. Exam 3 is more down. Like the third exam will be easier than this one. So I think about 5.1, which is a good way to start, is I'm going to sing hooray for dot products. You guys remember what a dot product is?
Yeah.
If I want to do, that's what we can use it for. So how do I do the, what's the dot product of 1, 2, 3? So the actual calculation is I do 1 times 3 plus 2 times 4, which is 3 plus 8, which simplifies to 11. So is one fact that we had. How can we tell if V is perpendicular to W?
The dot product is equal to 0.
Very good. So I'm just going to spend several minutes telling you everything I like about dot products. And one thing I like about dot products is they're perpendicular detectors. So if I take a dot product and get 0, that tells me the vectors are perpendicular. Let me show you another thing I like about dot products. Is what does the double bar mean? The magnitude. Which is the fancy way of saying length. Then the magnitude essentially comes from the Pythagorean theorem. So the vector looks like 3, 4 up like that. I'm going to break this down. Do 3 in that direction and 4 in that. And then Pythagoras tells us that the hypotenuse is square root 3 squared plus 4 squared. But if we write this out a little bit, so instead of 3 squared, I'm going to write it as 3 times 3, instead of 4 squared, 4 times 4. Is this, looks like a dot product to me. It looks like 3, 4 dotted with itself. So I can also use a dot product to find magnitude. Because the magnitude of a vector is the square root of the dot product of v with itself. And this is something just take as a fact right now. If you have a little bit more time at some point, I'll try to convince you. Is I can compute cosine of theta with a dot product in 2 lengths. And can you compute lengths with dot products? So, or another way we could say it is theta is the arc cosine so it's really, if I go through the derivation, it's really the law of cosines. Black box that, you can trust me. So I can find angles with dot products. So even better than just a perpendicular checker, I can actually find the angle. And let's check out a little bit more about this. So do you know that the lengths or the magnitudes of vectors are always positive? And if I have a first quadrant angle, is cosine positive or negative?
Positive.
And if I have a second quadrant angle, cosine is. So if I end up with a first quadrant angle here, cosine is going to be positive. A second quadrant, cosine is going to be negative. And the bottom is guaranteed to be positive, so it's just the top that's going to determine whether it's positive or negative. So what I have so I can use my dot product as a perpendicular detector. If I get 0, another perpendicular. But if it's not 0, it's either positive or it's negative. The positive means cosine was a positive number, which gives me a first quadrant angle. If the dot product is not 0 and it's negative, that must mean that cosine is negative. I got a second quadrant angle.
So do we get other like sine, other sine and other ones?
No, with dot product. So for your Calc 3 fans, do you know about cross product? So cross product has a sign. What's better, dot product or cross product? Dot product. So dot product will work with any dimension. For you Calc 3 people, cross product only works in dimension 3 and dimension 7. Like dot products in more general. Some more stuff I wanted to do, show you about dot products. Give you some more vocabulary first. Don't these always start off easy? We'll get harder. First lecture of each chapter. Straightforward. thing is I know my U's and V's look similar. So I try to use V and W when I'm talking about generic vectors. Those are easy to keep apart. And U is I'm going to reserve for a unit vector. What does it mean for something to be a unit vector?
It's negligible. So it's a V?
That is a U.
You can square both sides.
So if it's a unit vector, a good way to check is to just take the dot product of the vector with itself. More words? This would apply to any set of vectors, but we're always going to refer to bases with this. So some bases are nice. So this could go up to any size n. I'll show you three of them. So two words is some bases are orthogonal and some bases are orthogonal. So orthogonal are U1, U2, and U3 are all perpendicular to each other. And then orthonormal means orthogonal plus every one of the vectors in the basis is a unit vector. So orthogonal means they're all perpendicular to each other. Orthonormal means they all have length. So I'm going to show you why we like orthonormal bases.
So they are all perpendicular and they all have a length of line.
Absolutely right. So orthogonal means they're all perpendicular to each other. Orthonormal means they're all perpendicular to each other and each one is a unit vector.
Both cases are unit vectors, right?
The bottom.
The bottom.
So the top is just perpendicular to each other. Let's imagine I want to write the vector 5, 1 as a linear combination of 2, 1 and 1, negative 1. Is B an orthonormal basis? basis? It is not. It's not length 1 and perpendicular to each other. So what you want to do is find an x and a y to make this equation true. Good. And then how do you do it? So you're right. So what's the process? Yeah, you got a system of equations. And then you solve the system. How do you solve the system? Augmented matrix, elementary row operations, reduced row echelon. And you can imagine regretting that I made this one so easy. I could have had a bunch of different vectors here, and it would have been a long equation.
You can have, I mean, you gotta run into the basis, I remember.
Sure. So I'm going to show you how easy this problem is if we have an orthonormal basis.
Can any orthogonal basis be turned into an orthonormal basis?
Yes, it can. You guys believe that? So if I, and we're going to talk about this, if I have an orthogonal basis, you see I can just stretch or shrink the vectors to make it orthonormal. So the orthogonal part is the hard part. Once it's orthogonal, it's easy to convert it to an orthonormal. So imagine I'm giving you an orthonormal basis. Unlike this one, I can actually give you an orthonormal basis. And is I'm giving you some target vector W, like I gave you here, 5, 1. And then what I want to do is write W combination of U1, U2.
Dot W with each unit vector?
Perfect, yeah, that's right. So what I want to do is I want to find scalars for U1, U2, and U3. So I want to figure out how far to stretch each of those unit vectors, and then add the stretched vectors together to get W. And normally I just leave the blanks there, but this time I'm going to do some algebra with this. So I'm going to call these numbers C1, C2, C3. And the nice thing is, when I don't have an orthonormal basis, or the way that we've been doing it, is I've got to set up a system of equations, and I've got to find each of them. Well, I solve the system, and then I get the answer for all of them. Because what I'm going to do here is we're going to get a way to do these one at a time. So watch this. And I'm going to be a little bit sloppy with how I do it, but every step that I do is actually allowed. So I'm going to dot both sides by U2. I'm going to distribute this in. That's U2 in. Take a second to catch up with me, or, as you can probably see where this is going to go. Yeah, so what's U1 dotted with U2?
0.
0, right? Remember I said this is an orthonormal basis, which means but U1 and U2 have to be perpendicular. And what about U2 dotted with U2?
1.
That's going to be 1. Because that normal part refers to the fact these are all unit vectors. And for a unit vector, when I dot it with itself, I get 1. And that's going to be 0 again, because they're perpendicular. So this is C2. So turning it around, I was trying to find C2, and it's going to be W dotted with U2. As I could also do it, how do you think I'm going to find C1?
W dot product U1.
And C3, I know you know this. So what I can do is I can find those coefficients directly. I don't have to set it up as a system of equations and solve the system. I think. Let's do an example with this. Out of all those great things I showed you about dot products, I think this is even better than all of those. Okay, so I'm going to give you a basis. It's first vector 3/5, 4/5, second vector -4/5, 3/5. Do you believe that's orthogonal?
Yes.
Good. So if I do the dot product of these, I get -12 over 25 plus 12 over 25. And do you believe that each of those are unit vectors?
Yes.
Yeah. So it is orthogonal. I'm not trying to trick you here, it really is. And then, I have 10, 15. Is I want to write it as a combination of these basis elements. So the long way to do it is call the first number x, the second number y, get a system of equations, row reduce it. But I've got an easier way now. What is the best linear algebra operation? Dot product. So how do I use the dot product to figure out the number that goes here? Is I take my target vector dotted with that vector. So what's that? 30 over 5 plus 60 over 5, which is 90 over 5, which is 18. Yeah. So again, it's just like we did before. I've got my building blocks, and I want to use those to build a target vector here. So I need to know how much to stretch each of these by. And what the dot product is doing for us is giving us a faster way to get that stretching factor. Say it again? Yeah, this is given. So remember, the problem is I'm going to give you an orthonormal basis, and I'm going to give you a W.
I'm so sorry. How do we know the unit vector again for the x and y? So do you have to dot 3, 5, and 4 times there?
No.
Oh, you dotted that. Okay.
0.
Go?
Yeah.
No.
1.
Yes.
Little one.
We go? And I'm not trying to trick you, so if I say it's orthonormal, it really is. So everybody good with the 8, how I got the 18 there?
Yeah.
Okay, and then,
1.
very good. It's the way I find that second coefficient. Instead of having to solve the equations, I just do a dot product. Negative 40 over 5 plus 15 over 5.
10, 15, not 10, 5.
Huh?
W is 10, 15. No.
Oh, it is. That's what I said. So it's negative 8 plus,
9.
there you go. So again, that's essentially what we're doing, is we've got an orthonormal basis now, which is a nice basis to have. I've got a target vector I'm trying to build with these basis elements, and I've got an easy way to find the scalars.
Question then, is it right to think of that scalar we come up with as the magnitude of our 10, 15 vector projected onto 0, 5, 4, 5 vector?
Let's say this. So if I was doing a perfect lecture, like I was actually going to set this up and these were going to be published officially, is I would pay people to ask the right question at the right time. So that is exactly the right question at the right time. Let's talk, yeah, I know. The check is in the mail. Let's talk about what's going on here. So remember, is we can think about a basis as a new coordinate system. So think about this as an x hat and y hat system. So here is my original xy. And then my x hat goes up this way. And my y hat goes up that way. And then it's, let's see if I can use a nice bright red or orange for this part. And it's here. In 15. And remember that 1015 is relative to the standard basis. So if I put the tick marks on here. Okay, then what we worked out is that if instead I want to get to that vector along x hat and y hat. Well, how far do I go along x hat?
18.
That's exactly what that 18 represents. So 18 along the x hat. And then how far along the y hat? So it's the actual vector. This picture is getting a little crowded. You can see it. Is the actual vector is like this, which is the new coordinates are how far along x hat and how far along y hat. So do you see that it's this 18 is the length of the projection onto this? So if I had just asked you to do a projection, we wouldn't even need to complete the whole basis. So it's my next example. We're going to be doing a projection. We've done this a couple times already. Do I have one more? what I want to do is I want to project the 1, 1 vector onto the line y equals 2x. Let me draw a picture. So I think to myself, we did something similar already. So this is yet another way to do this problem. Is I'm going to make a new basis b. That's going to be my x hat and my y hat. And then, for that new basis b, here's my x hat, there's my y hat. And then, I just want to figure out, so here's 1, 1. I just want to figure out how far along I go on the x hat. So on my new x-axis, the projection is just how far along I go in that direction. Okay. That's the point 1, 1. We're projecting it onto this line. Okay, luckily, is all I need to know is the vector that corresponds to x hat. And as long as this is an orthonormal basis, I can find that projection just by doing the dot product. So I want this, so I want x hat to be the y equals 2x line. And I want that to be orthonormal. So first of all, can you give me some vector on the y equals 2x line?
1, 2.
How long is that?
Square root of 5.
Yes, so that's too big. So how do I shrink it down so it has length 1?
1 over.
It's 1 over square root of 5, 2 over square root of 5. So it doesn't even matter what my y hat is. That's going to be my x-axis. And knowing how far to scale that tells me the projection of 1, 1 onto that line. Was it? Oh, did you get it already? So I have no idea. I believe I can work it out. So what we do is we get that 1, 1 is blank times 1 over root 5, 2 over root 5, plus blank times. And we're not even going to worry about this part. So this is our x hat. The nice thing is if we're doing a projection, we know how to do each component. So I showed you the secret. Is how do I find how far to move along the x hat? Got it. So, you agree with me? Hooray for dot products?
Yes.
Hooray for dot products. I'm going to go 3 over root 5. Oh, because I just want to find the projection. So that's how far I move along the x hat. Okay, what did I just compute here? That 3 over root 5 represents what? That's not a vector. It's just a number. What am I going to do with that number? Okay, this is how far I move along the x hat axis. So this is going to be the projection onto y equals 2x. So now let's actually do it. You agree 3/5, 6/5? No, so that is just me,
Oh, sorry.
just me doing this. And another way to say it is what point on the line y equals 2x is closest to 1, 1? And that would be exactly what we have here. Point 3/5, 6/5. If I want to get to 1, 1, I have to stay on the line y equals 2x. That's the closest. Stupid.
Is there any difference between this trading and you use projection function?
Yeah, so we've done this, I think, 3 different ways, or we've done this this is our third way, right?
Yeah.
And then you can use trigonometry as well. So they'll all get you to the same answer. I think this is the easiest out of all of those. So, you know, at some point we start running out of math problems, so we'll just show you more ways to do the same problem. You've got an issue coming up, I haven't even thought about it yet. Does this class feel like a lot of work?
Medium.
Okay, medium, good.
It's not like the most work, but it's not the easiest.
Good. I'm glad to hear that. Because I'm worried, it feels to me like this should be more than a 3-unit class. Like we cover a lot of material. And it's very political. I've actually tried for a while to get it to be a higher unit class. And just the opposition.
What's the difference? Like it's high.
I get more time to lecture. So just longer lectures, so it's a little bit slower.
Yeah, it's better.
I agree. Okay, but as I was talking to some of your teachers, and they actually felt bad for you. So they said that they were willing to cancel all of their Thursday classes if you stayed home and studied linear algebra. So you didn't have to come to school on Monday, you could just stay at home, study linear algebra, and get caught up a little bit.
Oh, this Thursday, right?
This Thursday, yes. There's one bad thing, is I try to keep the Monday, Wednesday, and Tuesday, Thursday classes the same. So that means that the Monday, Wednesday class gets 2 lectures to their 1 lecture. So I don't want to go racing too far ahead of them. So on Wednesday, I'm not going to prepare any new material. That's going to be your chance to ask me any questions that you've got. So if you want to ask me about homework questions, I'm good with that. Oh, and homework is due that night, right? So you might have some questions for me. If you want to go, what's that?
This Wednesday?
Yeah, day after tomorrow.
Oh, every Wednesday also.
No. The Wednesday, that's, I guess, I don't know what the word is, the day after tomorrow. Overmorrow, I think that's called. What if, you don't have any questions for me? Yeah, I'm just gonna kick back. I'll do some math on my own. Wednesday, I don't have anything prepared. If you want to go over the exam, you have homework questions. You want me to talk about Rubik's Cube. You want me to talk about some cool applications of linear algebra. So I'll talk about anything you want to talk about.
You just hang out and study?
Oh yeah, we can do that. So just hang out. Sometimes it's a good thing to do with off there. Just hang out, study. If you've got questions, call me. I'll help you out.
Bring some pizza and
You can bring some pizza. So you're
I
gonna
don't need.
Okay, so I am going to look at a 2-dimensional subspace of R4. R4 has 4 mutually perpendicular axes. W is some two-dimensional subspace. And as you're copying this down, it's verified to yourself this really is orthonormal. This is an orthonormal basis for W. Do you agree?
Yes, sir.
Then, let's do a good picture. This is good of a picture. So here's W, which I'm thinking is some subspace of R4. And then that notation. Is I've got my vector W out here. Then what I'm going to do, I want to give a name for this. I'm going to call this W parallel. So W parallel is going to be the closest vector in W, the closest staying in W, getting as close as I can to the given W vector. As I'm erasing, I'm going to tell you an interesting story. So some math teachers were friends with some English teachers, and the English teachers were complaining, rightfully so if you ask me, about all the papers they had to grade. And linear algebra teachers said, you know what, I bet you could use linear algebra to do the grading for you. So what they did was they devised a way to turn a paper into a matrix. And they did it by counting words in various ways. And then, so they looked at the space of all papers, and then they took the what they called the gold standard papers, the A+ papers, and made that a subspace. And then, when you get a student's paper to grade, this is going to be a vector sticking out like this. And then you're going to look at the angle between the given vector and the projection. You know how to do that with cosine, with dot products. And if this angle is 0, it's in the A+ space. If this angle is almost 0, it's probably an A paper. And then, as this angle goes from 0 to 90, maybe 45 degrees is a C minus. The bigger the angle, the worse the paper, and the lower the grade. So they actually passed out the papers. They picked, I think it was 5 English teachers and their program. And then they asked the English teachers to assign a grade to the paper and compared that to what their program did. And their program was consistent. Where the English teachers scored high. I mean, some teachers might say A minus, some might say B+. But the linear algebra grading was about as good as the English teachers. Many things that we can do with linear algebra. Is if this is my W, do you know how to find the projection of W onto this subspace? So if W is the span of this, that means that anything in W can be written as a combination of these basis elements. Oh no, it's W, this is my notation for the projection of the vector minus x.
Notation for projection of W on the W space.
And I'm regretting my name choice already. So I just need to find the coefficients of those two vectors. So I need to know how far to stretch each one. So how would I find the coefficient of the U1 vector? Perfect, yes. That's exactly what dot products do for us. So if I do my given vector dotted with U1, that's going to be the magic number there. And I got 2, 4, 6, 8. Conveniently, I chose even numbers. So that's 1, 2, 3, 4, which is is it okay if I don't? No, wait, is that true? Or should be yes. Okay, if I don't do the arithmetics. And exactly. So the nice thing is with an orthonormal basis, I can use dot products to figure out these scaling factors. Is it really 0?
Yes.
Oops. Oh well. Bad choice. I get 0. Okay, so actually maybe it's not a bad choice. Leave this in your head. What's the actual vector?
5, 5, 5, 5.
5, 5, 5, 5. Yes. 5. So again, I've got this vector 2, 4, 6, 8 that's hanging out like this. And if I'm restricted to stay in W, is the closest I can get to that is 5, 5, 5, 5. There's no vector in W that's closer than that one. I want to see what happened. I copied the B down. That is it for 5.1. I've got a vector 2, 4, 6, 8. I want to project it, same vector I had last time. I want to project it onto the W space. And my W is going to be the span of 1, 1, 1, 1, and 1, 9, 9, 1. So you know how to do this with an orthonormal basis. Is that an orthonormal basis? No. It's not, unfortunately. So 5.2, we're going to talk about the process of taking a basis and converting it to an orthonormal basis. Let me draw a picture of what I'm going to do. And then we'll actually go through the arithmetic. You give names to these. So there's V1, there's V2. So this is what we've got. We've got V2 out like this, V1 out like this, we got V2 up like that. And we go step by step. Is first thing, we need V1 to be a unit vector. Is it? Okay, what's the length of this? It's 2. So the first thing we're going to do is shorten V1 U1, so it is a unit vector. Now, we're going to think about V2 as, it kind of has two directions in it. It's got a direction that's already in the direction of U1. And it's going to have a new direction that's perpendicular. So we're going to break V2 into two pieces. I'll call it V2 parallel and V2 perp. Then, I've got my U1 here, and my V2 perp is up like that. So do you believe that anything I can build with V1 and V2, I can build with U1 and V2 perp? So V2 has, so if I use V2, it's, part of that's just going to be some U1s. So I can do those into the U1. And then I can build the rest of it with this part. And then, as the last step, U1's going to be here. And this might be too long, so I'll shrink it down to give me the unit vector. So again, that step-by-step process is I'm giving these two vectors. First, shrink U1 so it's a unit vector. Break V2 down into a parallel part and a perpendicular part. The parallel part is the projection. And if I know the original vector and the projection, we get the perpendicular part. Take the perpendicular part and shrink it down so it's a unit vector too. Let's go ahead. Yeah, we've got time.
What's the second vector?
1991. First thing I do is I make that vector, I check the length of that vector. I wish it was a unit vector, but it's not. It's too long. It's only 2. So my U1 is going to be the scale version of that, which is half, 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 half. So let's keep track of our answer over here. Remember what I'm doing is I'm saying I really wish I had an orthonormal basis. So I'm going to change the basis, so it's still a basis for the same space, but now it's going to be orthonormal. So everything that I can build with V1, I can also build with U1. Now, I'm going to find the parallel part of V2. Exactly. So that's just part of V2 that's in the same direction as U1. So that is the projection. No.
Oh, we changed it.
Exactly. So as long as that's a unit vector, do you know the shortcut for figuring out the scalar needed for the projection? What is it? Oh, there's no W here. Good. It's going to be V2 dotted with the U1. So my V2 is 1991. Perfect. Where did I have myself? 10. Everybody agree with 10? So I get that the V2 parallel is 5, 5, 5, 5. And notice is this picture over here. Is the way I get V2. I can break V2 down into its parallel part plus its perpendicular part. So what I have is that V2 is the parallel part plus the perpendicular part. Or maybe a better way to write that is to get the perpendicular part, I do all of V2 minus the parallel part. Because when we come to the same thing, is how do I turn a 5 into a 1? How do I turn a 5 and so my V2 work is -4, 4, 4, -4. Is that perpendicular to this one? You can check the dot product, or just by the way we constructed it, it has to be. I'm almost happy with that. What's my problem? Yeah, I want it to be a unit vector, it's too long. So can we fix that? Magnitude, this guy. Is square root -4 squared plus 4 squared. 8? I'm glad you're here. I'm serious. This is a word. I'm going to have to do it, and then probably more times than not, I'm going to make mistakes. Everybody agree with 8? Yeah, I do. I'm even not going to check it. That is right. So I wish that vector had length 1, but it really has length 8. So how do I cut it down, guys? Yeah, if I just take 1/8 of that vector, that's length 2. I was talking about doing projections. I gave you a vector. I gave you the space I wanted you to project it on. And unfortunately, I described the space with a basis that wasn't orthonormal. So what I did was I found another basis for that same space that is orthonormal. And then I know how to do that process with this orthonormal basis. So remember, Wednesday is I'm happy to talk about whatever you want me to talk about, but if you don't have anything for me to talk about, I'll assume that you're all good on linear algebra.